contact with him was reading Russian translation of the algebraic eigenvalue problem. That was hard. So my talk today is a little bit related to high accuracy and backward stability, and I think it is appropriate for this meeting. 3 topics given the time limit are symmetric eigenvalue problem, SVD, and something with QI pivoting. No need to introduce backward stability to this audience, so we want to justify the output by somehow providing a slightly changed input that would somehow reproduce in exact computation what we have computed numerically. And then, depending on the space where X lives, we may want to measure this in different ways. Operator norm, entry-wise, column-wise, row-wise. We want to preserve structure. There's a symmetry. We want to keep it. And there will be condition number that will somehow try to estimate the distance from what we have to this exact value. So it's on yellow in purpose because you barely see it. That's how it looks like in real life. You don't know where it is. We start with the problem that we know that's perfect, well-conditioned, everything is beautiful, symmetric eigenvalue problem. So the spectrum is real, the eigenvectors are orthonormal, algorithms are based on unitary orthogonal matrices, backward stability is there, so everything is perfect. And then we take one example, 3×3 MATLAB. So this is a 3×3 matrix, MATLAB, Eig, 1 positive, 2 negative eigenvalues. If I ask Cholesky of this matrix, I get pretty decent Cholesky factor. So now the question is, oh, this is backward stable, this is backward stable. Is this matrix positive definite or not? Because these two contradict each other. Although this is orthogonal and this is non-orthogonal. Now try to compute this spectrum. So this is the Eig. Now if you apply congruence by any permutation but identity and take Eig, we get these 3 numbers, positive definite. If you compute numerically the inverse of this matrix, then Eig, then invert the eigenvalues, you get these numbers again. If you take inverse numerically twice and get Eig, you get again these numbers. If you change the initial age by flipping the sign of the second largest entry to the diagonal, you get the same spectrum as before. If you introduce just one rounding in 1, 3, 3, 1 positions, you get this spectrum. Now by backward stability, all these numbers, all these spectra are acceptable. It's backward stable. But obviously something is kind of weird here. Now back to backward stability. Okay, unitary, backward stable. Weil's theorem tells us, well, the change in the eigenvalue cannot be bigger than the change in the matrix. That's also beautiful. However, if you compute the relative error, then you see that the smallest eigenvalues get somehow, the error gets multiplied by the condition number. So there will be amplification in the small eigenvalues, and there will not be computed to high accuracy. Now the question is, can we do better than this? Now a little bit perturbation theory, different from the Weil's theory, but somehow related, tells us that basically if there's a perturbation so that the definiteness remains, then you can show by Ostrovsky's theorem that the relative error is bounded by this quantity. And this quantity, once you analyze it, you see that it depends on this delta H sub s, which is perturbation divided by the square root of the diagonal. And the condition number, this inverse H sub s, is the matrix you obtain by taking the inverse of the square root to the left and to the right. So it has a unidiagonal. Now in these terms, the relative perturbation is bounded by this scaled condition number, which is nearly optimal, times the perturbation with entry-wise scaled entries. So if we could provide an algorithm with the backward error that's small in this sense, then this would be condition number. If the backward error is small only in this sense, this would be the condition number. And that's the Wonders-Lewis theorem. So for this matrix, after scaling, its condition number is 1.4, not 10 to the 40. But it is 1.4 if the perturbation is small in this sense. So if we could have an algorithm that produces this small, in this sense, small perturbation, it would be okay. Oh, there is one. A simple method, like very old, Jacobi's method. it applies a sequence of orthogonal transformations to the left to the right. Somehow it keeps eating the off-diagonal entries and feeding the diagonal. So in the limit, the matrix will be diagonal, and it's been 1992 paper by Jim Demel and Krešimir Veselić proved it is more accurate than QR. Precisely in this sense that this is the condition number and not this. So this is a big difference. This applies to the SVD as well. So we can compute SVD again by Jacobi SVD by doing implicitly symmetric Jacobi. So this is also well known. And again, you can make it block oriented, like BLAS3 based. And again, it is you can prove that it is kind of it produces better structured backward error. So if you apply it to the symmetric eigenvalue problem by doing Koleski and then SVD of the Koleski, but by the Jacobi SVD, you can prove that the backward error is indeed entry-wise small. And this entry-wise backward error is n times epsilon. Really, so this big O here, the big O means that there's a number of sweeps, which is like a 50 at most. So this is really tight. And then we can apply it as a full SVD, and it has many nice details. You use the theory of quasi-definite matrices, entropy-based decisions in the algorithm, and so on. And again, at the end, you show that the error in the output is bounded by the condition number of the scaled matrix, which means that if I have A and if I can write it as B times D with D diagonal and B well conditioned, the accuracy will depend on the condition number of B. If you apply here full pivoting in the QR, then you have invariance on the two-sided scaling. So no matter what the condition number is, if there are D1 and D2 that will make it well conditioned, you will get the accuracy that is governed by this condition number of this C. So that's a big advantage. And again, there's a error analysis that basically proves that the condition number of the scaled matrix is possible if your backward error is small in this more localized sense. So that's a big advantage. To show how this looks in practice. So this here, these stairs, each stair corresponds to a set of matrices with the condition number of this scaled matrix fixed, like 100,000, 10,000, and so on. And for each class of kappa of B, we apply many different Ds just to increase the condition number. And we'll see that for each fixed, let's say this stair, inside are matrices with a really high condition number, but the scaled condition number is fixed. So this is the green is the measured error, the red is the theoretical upper bound. And if you just remove the factor of the dimension of this upper bound, that's usually the worst case, then we get this purple line which really matches the measured error. So everything is really tight. On the other hand, if you apply the QI SVD, then for this fixed scale condition number, the error goes up to 10 to the 10th relative error. Because every diagonal scaling that increases the condition number will just spoil the accuracy of the SVD. How far we can go with this is, just give you one example, really extreme. Hankel matrix given as a product of Vandermonde, diagonal Vandermonde. So we apply special techniques for this. This is a work initiated by Jim Demel, basically with Vandermonde and Cauchy matrices. So this is one example of a matrix, Hankel matrix with a condition number, well, 10 to the 615th. And this is ordinary double precision IEEE. So we get 13 digits of, using in ordinary 64-bit arithmetic, we get 13 out of 16 digits accurately. Although the sigma max is 10 to the 306, and sigma min is even slightly denormalized. So you can work a really wide range in lower precision, provided you use appropriate algorithm. Interestingly, QI-SVD, recently we managed to somehow to fix it in the sense that if you pre-process or precondition it by QI column pivoting and then do SVD, QI-SVD, it gets as accurate as Jacobi. We cannot prove it as yet, but the results are really, this is like a picture as before, only the blue is this new QI-SVD. Again, the error is bounded by scaled condition number. Even the singular vectors, they depend on the most recent perturbation theory, relative perturbation theory, relative gap, everything matches theory perfectly. So basically, the message here is we can compute SVD better than condition number of A tells you. So that's the important thing. Now, QR column pivoting. It's been mentioned many times today. And we pivot in a way that in the QR factorization, the diagonal in R is monotonically decreasing in absolute value. And then every diagonal entry will dominate the norm of this subcolumn. This is the result of pivoting. And we use this in our SVD as a preprocessor. And then the SVD at some final stress test, our SVD code failed. And then in the post-mortem analysis, somehow we realized it was a problem with QR column pivoting in LAPACK that we used. Backward stability for this is perfect. It's perfect for the classroom to prove backward stability. Lots of commutative diagrams coming together. Everything is backward stable. But if you check the output, this what defines pivoting, we found at first only one example where this relation failed. Then we studied it, and then we realized we can make many such examples. So this is MATLAB 2006. Remember, the red is diagonal decreasing, blue is the off diagonal. So we had an example, diagonal decreasing, and then started increasing. And this dominance failed. Now that you found one, then you can make many. So that's how mathematics work with counterexamples. That's why we're afraid of them. If there's one, there are many. So another example again. Monopoly, then something happens, then again. Consequences. Let's say you do least squares in MATLAB. You get rank 3 or 4, although the rank is 466. So in the least squares, you mix like 150 dimensions just because this is the diagonal of R, so this is the first moment at 3 or 5 where the first diagonal entry touched the threshold, and then backslash assumes the rest is even smaller, it would truncate. But it is not small, it just rebounds and so on. Then you just look at LAPACK or other packages, then you see many routines that depend on QR column pivoting, you can make them fail. So for instance, the Zlatko library, we managed to break 60 out of 470 routines. GSVD, least squares, and so on. Okay, this didn't go well. So Kahan mentioned that this is the longest instance of like an undiscovered instability that's been around since 1965, since the first code of LIMPACK, basically. And what's problematic here, we managed to manipulate the rank of a matrix by inserting the right statement. So you can insert the right statement in the source code, and the rank of the matrix will change. That's very tricky to explain. It takes you, it's not a bug, it's instability. So that's a problem. And so basically, we managed to fix it in 2006. So since LAPACK 3.1, it's been fixed. So this is one example from the Zlatko library. The rank is 49. You insert the right statement, is 82. And you compute staircase of dynamical systems. Everything is just gets wrong. So we managed to somehow find how to fix it and so on. There's a proof that now it's probably safe. And then every other packages that relied on LAPACK would automatically get the fixed. But some other packages just copy-pasted that problematic part of the code. So they are not, they still have this problem. So for instance, LAPACK, QR column pivoting, still if you insert the right statement here, you can manipulate the rank of the matrix in LAPACK. And then every other routine that will use QR column pivoting, you can make it fail miserably by inserting the right statement. And that right statement, it's precisely one place in the code when the critical variable is in the long registry in the CPU. So if you want to write it, you have to spill it out to the working precision. You lose that extra bit, everything's gone. And then this is very critical. So I think it should be fixed. It's about time to fix it in LAPACK as well. So I finished with a few conclusions. So doing orthogonal or unitary transformations, somehow we get very easy backward stability in matrix norm because unitary doesn't amplify the error, so you just accumulate them, everything is fine. So that's not good enough. We can do much better than we think that, when we used to think that it's possible. And then two quotes that actually makes everything this somehow make all these messages very compact. We can do much better than it's doing it by routine numerical analysis in terms of backward stability, and it is just an insight, not the end of the story. Thank you.
So do you have any questions, Jack?
Sorry?
Do you have any questions?
Do I have any questions? It sounds like we need to do some fixes to our code, especially before the new stuff gets let out. So we should definitely talk about where to impose the fixes and how that should actually be done.
Yep.
Do you have a question?
Please.
So for the ill-conditioned eigenvalue problem, were you advocating doing the Cholesky decomposition first?
For the positive definite case.
Yeah, that's what I meant.
Yeah, for the positive definite case, I think this is the best you can do.
Right. I was concerned that you're assuming it's ill-conditioned. So would it Cholesky break down?
So if you make this scaling, so this matrix has a 1 and hij square root hijj.
Mm-hmm.
So if the condition number of this matrix is bigger than one of the machine precision, then there's a theorem that tells you that you can make epsilon big rounding errors in your matrix entry-wise. Just flip the last bits of the mantisas over the entries to make it indefinite. So in that case, if that condition number prevents you to compute numerically to high accuracy, then your matrix cannot be considered numerically definite, because flipping the last bits of the mantissa can make it indefinite.
Right. Okay.
Okay. And then the overall error of this computation is this n times epsilon times that condition number. So basically, you are very, very tight with this.
Okay.
Yeah.
So that brings me back to a discussion that we had before. If you're in that situation, you should do a regularization to your problem, because if your original problem was positive,
Right. Yes.
definite. So I think this is something also in the whole discussion we should reconsider. We should not use the black box, but we should ask back, where does the problem come from, and if this is supposed to be a positive definite problem, then we should do the regularization first.
Yes. I think that's why I put this example with the Hankel matrix. Yeah. Hankel matrix, as well as Toplitz's matrices, there's a theorem you cannot compute accurately. Once you have it in a machine, you're doomed. But here, if you know a priori, in many cases you do know that your Hankel is Vandermonde times diagonal times Vandermonde. So if you parameterize the matrix, the Hankel matrix, by the parameters of the Vandermonde and the diagonal, and you work with the two vectors of parameters, you can do whatever you want. Once you store it in the machine, you are done. So that's correct. If you know it's definite, then you know it's factor a priori very easily.
Other questions? Okay, thank you so much.
Thank you.
So,